We summarize on this slide the different hypothesis setups for testing the mean or testing the proportion, including in each setup their respective decision rules. In testing the population mean, one of two test statistics may be appropriate to use, the t-distribution or the z-distribution. The z-distribution is appropriate to use when the population standard deviation is known. When the population standard deviation is not known, the t-distribution should be used when the sample size is small, provided the sample comes from a normal population. Recall that in Chapter 5, we talked about the use of the normal distribution, a distribution for continuous random number, as an approximation to the binomial distribution, a distribution for a discrete random number. So for testing a population proportion, the standard normal distribution may be used to carry out the test when the condition n times pi and n times 1 minus pi are both at least 5. Now let's take a look at this example for testing a population mean with a known population standard deviation. Recall that in Chapter 9 we talked about confidence interval estimation for the mean when the population standard deviation is known. In that case, we use the z-distribution. So we're going to use the same concepts in performing the hypothesis test for this problem. Jamestown Steel Company manufactures and assembles desks and other office equipment. The weekly production of the Model A325 desk at the Fredonia plant follows the normal probability distribution with a mean of 200 and a standard deviation of 16. Recently, new production methods have been introduced and new employees hired. The VP of Manufacturing would like to investigate whether there has been a change in the weekly production of the Model A325 desk. A sample from last year's weekly production yielded a mean number of desks produced of 203.5. Test using 0.01 significance level. This slide and the next few slides show the 5-step procedure for carrying out a test on a population mean when the population standard deviation is known. The test will use the z-distribution since the population standard deviation is known. In setting up the hypothesis for the problem, the keywords are, there has been a change in the weekly production. The word change in this phrase suggests that a not equal to or two-tailed test is called for. This is reflected on the alternate hypothesis as the mean not equal to 200. The significance level is stated in the problem as 0.01. The test statistic for this hypothesis test is the z-distribution since sigma, the population standard deviation, is known. In step 3, we decided that the z-distribution is appropriate for testing the hypothesis in this example. On this slide, we show how the z-statistic is computed. The numerator in the formula obtains the difference between the sample mean and the hypothesized population mean. This is known as the sampling error. We divide this difference by the standard error of the mean, which is given as sigma divided by the square root of the sample size. Apply this formula on the next slide using the information provided in the problem described in the previous slide. In step 4, we formulate the decision rule. Based on the alternate hypothesis, the test will be two-tailed, meaning that there are two areas of rejection in the distribution, the upper and lower tails, as illustrated on the curve in this slide. The decision rule is stated as reject the null hypothesis if the computed z is greater than the positive critical z or if the computed z is less than the negative critical z. We use the standard normal table given a significance level of 0.005 to obtain the critical values of plus 2.576 and negative 2.576. These points mark the boundary between the reject H sub 0 and fail to reject H sub 0 regions. How did we obtain the critical z values given a significance level of 0.01? We will show this on the next slide. One way to obtain the z-value for a two-tailed test given a significance level of 0.01 is by using the standard normal table in Appendix B1 of your textbook. On the distribution curve shown on the slide, observe that the lower and upper tails of the distribution are 0.005, obtained by dividing the 0.01 significance level by 2 since the test is two-tailed. As such, the area from the center of the distribution, or z equal to 0, and the z-value corresponding to the upper or lower critical values is 0.4950. Locating an area equal to or closest to 0.4950 in the z-table yields a critical z-value of plus or minus 2.58. Another option, which is more precise, way to find the critical z-value is by using an Excel function. And the function is equal to NOR MSINV, and then in parentheses you put 0.995. So this function will yield a z-value of 2.5758, the upper critical value. Then to obtain the lower critical value, you're going to use the same thing, except you're going to put, instead of 0.995, you'll put 0.005. This function will yield a critical z-value of negative 2.5758. In step 4, we formulated the decision rule. We stated that we will reject the null hypothesis if the computed z is greater than the positive critical z-value or is less than the negative critical z-value. We obtain the critical z-value as plus or minus 2.576. In step 5, we compute the z-statistic using the sample results. We substitute the sample mean of 203.5 into x bar, 200, the hypothesized mean, into mu, 16, the population standard deviation, into sigma, and 50, the sample size, into n. We obtain a computed z-value of 1.55. We then make a decision and interpret the result. Because the computed value of 1.55 is not greater than the critical value of 2.576, we cannot reject the null hypothesis. So we conclude that the population mean is not significantly different from 200. In other words, we can report to the Vice President of Manufacturing that the sample evidence does not show that the production rate at the plant has changed from 200 units per week. Here's another example of testing a population mean with a known population standard deviation. But compared to the previous problem, the test in this example is a one-tailed, right-tailed test. The keywords in the problem are the mean number of desks assembled in the last 50 weeks was more than 200. The words more than translate into greater than. Because this is a one-tailed test, the significance level of 0.01 is at the right tail of the distribution. We show the hypothesis setup, the decision rule, and the choice of the test statistic on the next slide. In setting up the hypothesis, the key word in the problem is the word increase, which suggests that we want to test whether the average is greater than 200. This is the alternate hypothesis. The null hypothesis will then say mu is less than or equal to 200. The significance level was stated as 0.01, and since the population standard deviation is known, the appropriate test statistic to use is the z distribution. We show in the next slide how the significance level of 0.01 is converted into a critical value. So before we determine the critical value for the test, we recall that on the first time we solved this problem, we tested the claim as a two-tailed test. The decision rule for this test is illustrated on the left-hand side graph. Note that because the test was two-tailed, there were two areas of rejection, and they were at the tail ends of the distribution. We also noted that the significance level of 0.01 was divided into 2 so that each area of the rejection became 0.005. For this revised problem, however, we are performing a right-tailed test. As such, the rejection region is found on the right tail of the distribution, as illustrated on the right graph. Note that the significance level remains at 0.01. The corresponding critical value for a 0.01 significance level is 2.326. Instead of using the standard normal distribution table as we did in the previous problem, we can also use Excel to obtain this more precise value. We formulate the decision rule as reject the null hypothesis if the computed value of z is greater than the critical value of z at the 0.01 significance level. In the previous slide, we established the critical value as 2.326 at the right tail of the distribution. The next step is to compute the z statistic using the formula shown on the slide. Substituting the information provided in the original problem, we obtain a computed value of 1.55. Note that the computed value for this problem should be the same as the computed z from the previous problem, since we were using the same sample data. Since the computed value lies within the do not reject the null hypothesis region, we conclude that the population mean is not more than 200.